Good morning. Today I want to talk about one of the most difficult topics to understand in electricity, and that is the concept of voltage. So voltage is one of those things that we use in our everyday lives all the time, and we have no understanding of what it means. We know that we have to plug our devices into the right voltage, that car batteries have a certain voltage, certain types of batteries, 9-volt batteries, AA's, AAA's. We know that the US has a voltage, that most of the rest of the world has a different voltage. But what does that mean? That's what I'm going to try to explain today. I think it's one of the most misunderstood concepts in physics, and hopefully this will clear it up. So first of all, we have to be careful about vocabulary. We use the words voltage to describe something that physicists call something different. They call it electric potential. So I'm probably going to use the word voltage because this is what the rest of the world uses. But when you're in your physics book, when you're talking to a physicist, that's what they're going to use. What makes the actual word a little bit better is that it's missing something. When I say electric potential, I bet a lot of you want to add the word energy at the end. And it actually isn't. So that's something that I think is worth investigating and seeing how these two are related to each other and how they're different. So we've talked a lot about power when we were studying energy. And we came up with the idea that the power something uses is important in determining how much energy it uses, but also the amount of time that that device is run for. For example, a toaster is a fairly powerful device, maybe 1,200 watts to 1,500 watts, 1,500 joules per second. But in terms of the energy it uses per month, it's very low because a toaster is not on that often. A light bulb, fairly low power, but on quite a bit, might make up the difference and use more energy. The difference between electric potential and electric potential energy is kind of like that. Although the other variable in this case won't be time, it will be charge. So let's take a look at a battery. So I've got over here a 9-volt battery. It's got a positive terminal and a negative terminal. And what that means is that at the negative terminal, a chemical reaction is happening that donates electrons. At the positive, there's one that's consuming electrons. I'll hook them up to a light bulb. A light bulb is just a coil of wire. And it's in a glass tube, obviously. And when I hook this up, electrons are going to move through. The light bulb in that fashion. So how much energy does it use? Well, I think it should be pretty obvious. It uses more energy if more electrons go. It uses less energy if less electrons go. So we don't really have a good answer to how much energy does that light bulb use. Depends how many electrons go. So it's a little bit like power, although the key thing in this case is not time, but it's amount of charge. So it would be really useful if we had a way of looking at energy in terms of not how much total energy you get, but how much energy each charge gets. So that's what the idea of voltage is, or electric potential. And I'm sure this is still a little bit fuzzy. So I want to take a step back from electricity and go into gravity. So you know the equation for gravitational potential energy. It's PE equals mgh. And I'm going to define something called gravitational potential. We'll call it Vg for gravity voltage. And it's going to basically be potential energy divided by charge, or excuse me, by mass. We're doing gravity, not electricity. So what would that end up being? It would be mgh over m. And we get the obvious cancelization of mass. So we're just left with gravitational potential is gh. Why is that useful? Well, let's look at this classroom. It's got a floor. It's got different heights. And I'm going to specifically care about h equals 1 meter. And h equals 2 meters. So I've got 3 textbooks. And I want to take a look at what their gravitational potential energy would be at these 2 heights. So we've got big, medium, and little. So let's take a look. My big textbook it's going to have a potential energy that equals its big mass times 9.8 times the height. Now the height and 9.8 are not going to change because I'm using the big book. I could do my medium book. Its potential energy would be its medium mass times g times the height. And I can do my little book. And its potential energy will be its little mass times g times 9.8. So clearly these 3 guys are not going to have the same potential energy. And I think it's pretty obvious this guy's going to have a bigger one because the mass is bigger. This guy's will be medium, and this guy's will be small. And we can see that by dropping the books. If I drop this guy from a meter, I get a small bang. If I drop this guy from a meter, I get a medium bang. And if I drop this guy from a meter, I get a large bang. More of a thunk. But, although the energies in those collisions were different, part of the equation for calculating those energies was identical, the GH part. And we could see that in each case, the voltage, or the gravitational potential, was just 9.8 meters per second squared times 1 meter. And more importantly, if we go back to the definition of gravitational potential, we see that each kilogram of mass here arrived with the same amount of energy. The big book had more kilograms, so it supplied more energy. But inside it, each kilogram got the same energy in kinetic energy that each kilogram in the little book did. So that's so important I want to write it. Each kilogram of mass got the same kinetic energy. Okay, so what happens if I repeat the experiment? Well, we're going to see obviously more energy delivered. I will repeat the experiment, but I don't think it's a surprise to say that we're going to have twice as much energy in each case. So here we're going to have 2 m, that'll be its potential energy, GH. Here we're going to have 2 m GH. And here we're going to have 2 m GH. But again, every kilogram is going to get the same amount of kinetic energy. And how much would that be? 9.8 meters per second squared times 2 meters. Where we have a voltage of 19.6. Whereas here, we have a voltage of 9.8. So the key thing is that every kilogram of mass hitting the floor now will have twice the kinetic energy it did before. And I think we should be able to hear that out. We'll still see a lot more energy in the case of the heavier book, but in every case, every kilogram will have twice what it did before. So there's about 2 meters, small, medium, and large. So let's go back to electricity now. In the case of electricity, well, I'll do it over here. We have what's called the electric potential. It's just called V. And again, it's potential energy. But now we're dealing with, instead of mass in electricity, we use charge. So quantity of charge Q. And the reason this is important is that it tells us no matter how many charges flow through here, each of those charges arrives with a certain amount of energy. And that's what you need to make a device work. If a device requires low voltage, that means every electron going through it will need a relatively small amount of energy. If it requires high voltage, every electron going through it needs a lot of energy. And each device is set up to work with a certain amount of energy per electron. Now that's not what voltage is. Voltage is energy per coulomb. A coulomb is more than 1 trillion electrons. So it's potential energy per charge, but don't mix up a coulomb with an electron. But the bottom line is voltage is a measure of how much energy each charge has. If you don't give it the right amount of energy per charge, it won't work right. One final thing here. Sometimes people are surprised to hear that the Van de Graaff generator, so voltage of Van de Graaff, that it has about 500,000 volts. But I'm willing to shock myself with it. I probably would not be willing to shock myself with wall current, which is, in the US, 120 volts. Why? Why this and not that? It has to do with the ability of these two energy sources to make electrons move. So in the case of the Van de Graaff, if I rearrange this equation, I think we can see that energy equals the number of charges times the voltage. In the case of the Van de Graaff, even though voltage is really big, the number of charges is actually really small. And that makes the energy it delivers to me pretty small. So it can't hurt me. Wall current's a little bit different. It has a relatively small voltage, but it's capable of delivering a large number of charges. So it can deliver a lot more energy, and therefore is a lot more dangerous. I hope that clears up the idea of voltage. If it's not totally clear yet, be aware this is one of the toughest concepts to get. But it just goes back to this idea. If we want an electronic device to work, charges have to go through it carrying a certain amount of energy. Voltage tells us how much energy there is per charge.